Okay, we've talked about positive integers, which are the numbers we count with. And I've talked about how the natural numbers are also countable, so they're the same size, same cardinality. And the set of all integers are still countable, that's the same cardinality, it's countably infinite. Well, the set of rational numbers are, a larger set still, right? Where now instead of just whole numbers, we're talking about fractions. Turns out that set is also still countable. So even if you are talking about the entire set of rational numbers, all the fractions, that's still countably infinite. It's still the same cardinality as the natural numbers. And the way to prove that is a little more complicated because the fractions are harder to put in order, right? Because between any two fractions, you have infinitely many more fractions, right? So with the integers, at least we could kind of go back and forth between like 1 and -1, 2 and -2, and form this nice like lining them up kind of way. It's harder to do with rational numbers, but still possible. And I'm going to show you how it's done. And the key is to kind of notice that a rational number is basically like corresponding to a pair of integers. So there's this idea that the set of rational numbers Q is similar to a subset of integers cross integers. In the sense that like a rational number a divided by b is kind of analogous to an ordered pair a comma b, where a and b are both integers, right? That's the definition of a rational number. It's a fraction of integers. Now there's more on top of that. There's a little bit of complication here because b is not allowed to be 0, and then like some fractions reduce and are equivalent to other fractions, like 2/4 is the same as 1/2. 6/3 is the same as 2, and so on, 2/1. And so, yeah, it's a little complicated, but at least it gives us a way to kind of divvy up, organize the rational numbers. And so here what I have drawn is just the top left corner of an infinite grid. So imagine that this grid goes on forever, and in this grid will appear every positive rational number. So this grid here, this encompasses all of what we call Q plus. This is the set of positive rational numbers. Now, so I'm not dealing with all the rationals yet, just the positive ones. But having lined them up like this, where we have numerators and denominators, and so you see all these rational numbers here. Not all of these are different rational numbers. For example, 1/1 is equal to 1. 2/2 is also equal to 1, and so is 3/3, right? So we have repeats. These are all equal to 1 down this diagonal. Things like 4/2 are here, but 4/2 and 2/1 are the same, right? So there's repeats within here, but there's a way that you can sort of traverse through this infinite grid that had, it's infinite in that it goes off forever, but it does have a top left corner. You can traverse through this infinite grid along diagonals in a way that is systematic and is going to capture every single positive rational number and put them in a list in an order in such a way that you can line them up one for one in a one-to-one correspondence with 1, 2, 3, 4, 5, 6, 7, etc. And it goes like this. You start from the top left and you take 1/1. All right. And we're basically going to go diagonally in sort of that direction. And then when we get to the edge of our grid, we're going to go down and take the next number down and come sort of up and to the right. And every time we encounter a number, if it's a new rational number that you haven't seen before, then you are going to count it. So we go 1, 2, and then this is different. That's going to be a third one, and then we'll come back down and start here. This is still different, so that's 4. That's the same. So we're going to skip right over 2/2 and look up here, and 3/1 is different. That'll be 5. And you see what I'm doing is I'm counting them, right? And then you keep on going like that. 1/4, 1 2/3, that's new. 3/2 is new. 4/1. And then we'll come down here, take 1/5. We'll skip 2/4, and we'll skip 3/3, and we'll skip 4/2. But then we'll take 5/1 because we haven't seen 5/1 yet. And then you keep on going like that. 1/6. Let's see, you take 2/5 and 3/4 and 4/3 and 5/2 and 6/1, and you get 1/7. You skip 2/6, you take 3/5. You skip 4/4 and take 5/3. You skip 6/2 and take 7/1, and you keep on going like that forever, like etc. forever. And what that does is it produces by this sort of algorithmic kind of approach, going like that, and then either counting it or not counting it if it's identical to something you've already seen. Well, then by that sort of algorithmic approach, you can count all of the positive rational numbers. Like you're creating a bijection with positive integers by doing that. So this shows that the positive rational numbers cardinality is the same as that of the positive integers, or natural numbers if you want, either one. And then what you can do is you can say, well, the set of all rational numbers is just basically going to be the positive rational numbers union with the negative rational numbers, and then union with the set that just contains 0 by itself. That's countable, as shown, right? You can show that Q negative is countable just by taking, just by mapping it to Q positive, actually, by just multiplying by -1. So those two are going to be the same exact size. And then 0 is only one element, so that's countable. And we just had a theorem on the previous video about, I mentioned that the union of countable sets is countable, and therefore, so Q is countable as well. And that kind of that's not a full proof, like that I almost shouldn't even write QED, but that's not a formal proof. But this at least gives you an idea of how you can prove that the rational numbers are also countable. So okay, I'm going very carefully through all the different traditional sets of numbers because I want to build up to the real numbers. So in the next video, we're going to look at the real numbers and ask, are they countable?